Hello everyone, welcome to lecture 4.2, which is on curve fitting continued and interpolation part 1. So in this lecture, we're going to continue a bit of curve fitting, looking at nonlinear relationships, polynomial regression, and multilinear regression in terms of curve fitting. And then after that, we'll move on to interpolating, and the first part is going to be focused on Newton's interpolating method, which we will see later in the slides. So whenever we are doing some type of curve fitting, in the previous lecture, we looked at essentially just a linear trend of points, and we try to fit those points to a linear curve, and we showed how we can have equations for the unknowns, which is the slope and the intercept. In some cases, the relationship between y and x, as we see here, is nonlinear, and we need to basically deploy models that are not linear to fit the data. So in this case, we have an exponential kind of model where y equals alpha 1, where alpha 1 is a constant, times exponential function to the power of beta 1 times x, where beta 1 is the second constant in this equation. Again, this is another kind of model, which is the power model. And instead of the exponential, we have x here to the power of beta 2. Again, we have two unknowns in this case. And we also have the saturation growth rate kind of model where we have two unknowns, this alpha here and this beta, in this format. So how do we solve these types of kind of models using the linear kind of model that we developed in the previous lecture? So what we do is we transform the models and linearize them so that we could fit them using a linear kind of curve. And using that linear curve, we can find out what are the alphas and the betas, or basically the constants that are unknown in the given function. So for example, in A here, for this exponential function, we can linearize it by taking the ln, or natural log, of the left side and the right side. And what we would end up with is ln y equals beta 1 times x plus ln alpha 1. So here we can see in this kind of function, beta 1 is the slope, and then ln alpha 1 would be the intercept for this given model. Again, for the exponential, or sorry, the power model, if we linearize that, we would get a function by taking the log of both sides that looks like this. So we have log y equals beta 2, which is the slope, times log x plus log alpha 2, which would be the intercept. Similarly, in this last model in C, we can linearize it by taking 1 over the left side and the right side and rearranging to get the following equation, where 1 over y would be what we would plot on the y-axis, and 1 over x is what we plot on the x-axis, and then beta 3 over alpha 3 would be the slope, and then 1 over alpha 3 would be the intercept. So again, here, note for the other models also, we are plotting here log y with log x, and here we're plotting ln y with x. So depending on which equation you get after you linearize the model, you want to set what the y-axis should be and the x-axis should be in the data set so that you could basically fit it into a linear model using the equations we saw in the previous lecture. So here we have an example where we're using the power model. So we have y equals alpha x to the beta 2, and we linearize it by taking the log of both sides. And you can see here log y equals beta 2 log x plus log alpha 2. So again, we said this is the y-intercept, and this is the slope, and this is the raw data points, x's and y's. So to basically use the function, or the functions that we developed in the previous lecture, we kind of have to assume that this is our new y, in quotations, and this is our new x, again in quotations. So when we want to use the equations to solve, we want to find out what the y is and what the new x is to solve the linear model for these equations. So looking at that, we take the log of x, so this would be our new x. So instead of 1, 2, 3, 4, 5, now we have 0, 0.3, and so on. And then in terms of the y, we take log y and this is what we see here. We just took the log of every point here. So log 5 is negative 0.3, log 1.7 is 0.226, and so on. So after that, we deploy the function that we had, in the previous lecture, where we perform a linear regression, and we find what is the constant a and b, which is basically the slope and the intercept. So if we do what we did in the last lecture, so we take the sum of the x's, sum of the y's, sum of the x squared, and so on, and sum of the x times y, and use that in an equation, and using also n as the number of points. In this case, we have 5 points. We would get this equation here. You can try this on your own to kind of practice what we did in the previous lecture. So I'm not sure if you saw the laser, but this is the linear regression point here, and that's what we're trying to solve for. In this case, we get 1.75 as the slope and negative 0.3 as our intercept. So recall that this negative 0.3 is the log alpha 2, and this 1.75 is the beta 2. So if we wanted to solve for beta 2 and log or alpha 2, what we have to do is basically, beta 2 is directly what beta 2 is here in this function, because we don't have any logs here, but alpha 2 is given as log alpha 2. So if we wanted to solve for the value of alpha 2, basically what we have to do is take 10 to the power of log alpha 2 to get alpha 2, and then 10 to the power of negative 0.3 to get that alpha 2 is in fact 0.5. So we can plug the 0.5 back to this function, and then this beta 2 to this function, and we can plot it, and we would get this nice kind of power function that we see here that goes through, this nicely set data points. Again, here, this is the linearized version. So we had log y plotted versus log x, what we see here, and this produced a linear trend, and we fit this using linear regression to get this kind of equation here, which represents this smooth line that is drawn that goes through most of the points that we see here. So this is an example of using linear regression to solve a problem where we have a nonlinear kind of model, as we see here. So the next thing we're going to look at is polynomial regression. So similar to what we saw with linear regression, the main difference here is we have now these variables, such as this x here, which is to the power of 2. So instead of having everything to the power of 1, now we have a polynomial, which is to the order of 2. And in this case, we would have to solve this in a similar fashion by looking at the error, as we see here, and looking at the part of the RMS that we could basically minimize to find where the error would be minimized when we fit this to a set of data points. So just like in the last lecture, we're going to take the partial derivative of SR here with A0, then A1, and then A2 to get these equations here. And we set them equal to 0 because that would be where the minimum is. And then after that, we kind of rearrange them in a format that looks like a set of linear equations with certain unknowns. In this case, the unknowns are A0, A1, and A2. So this would be our vector of unknown variables. And then this right side would be kind of the B values. And then all of these that we see here, such as the n, the sum of xi, the sum of xi squared, and so on, are the coefficients that we put in the coefficient matrix. So here we see kind of the matrix form of this problem for m+1 equations with m+1 unknowns in this case. So we can see this, the reason why we have m+1 is because we start with a0 as we see here. So we have, m is the final variable that we need to find. So we add +1 because this is a0 and we're counting from 0 and not counting from 1. So in this case, this is nth order polynomial where we are solving, a set of data points, and based on the number of polynomial fit that we're trying to fit, we have to follow the order as we see here. So if I wanted to fit, a second order polynomial, then I would have 3 unknowns. If I want to fit a third order polynomial, right, then I would have 4 points. So it would be A0, A1, A2, and then A3. So M would be basically 3, and that would be the third order polynomial. Another way of using kind of this regression is also to fit multiple linear regression. In this case, we have these unknown variables x1, x2, and you could have x3, x4, and so on. And all of them are to the power of 1, and that's why we call it multiple linear regressions. In this case, we can kind of see a similar fashion where we take kind of the objective of minimizing the error, which is SR in this case, derived from the RMS, and we take the partial derivative in terms of the kind of unknowns, A0, A1, and A2, and set it to equal to 0, and then rearrange to kind of get this format, which is kind of a set of linear equations, and then in matrix form, we get this final format when we have a problem with basically 3 unknowns as we see here. So one important thing to note here is this is multiple linear regression and it's not linear regression. So if I ask you on an exam to perform linear regression, this is not what you do. You would basically use the method that we presented in the previous lecture and not this one. If I ask you for multiple linear regressions, then you have to follow this kind of format. And typically I would give you the equations or the matrices that you need to solve for a given problem. So here we have an example where we basically made the example by kind of setting a multilinear regression or multilinear equation, which is 5 plus 4x1 minus 3x2. Then we basically set points for x1 and x2, and then solved for y to get this data set. And then we worked backwards to find what is A0, what is A1, which is 4, and what is A2, which is -3 in this case. So taking these equations and solving for, what is n in this case? N is the number of points that we have. So we have 1, 2, 3, 4, 5, 6 points. So the matrix here that we're going to be basically developing is going to start off with a 6 here, which is the value of n, and then the sum of x1, which would be basically the sum of 0 plus 2 plus 2.5 plus 1 plus 4 plus 7, which is 16.5. And then, the sum of x2 is 14. The sum of x1, again, is the same here, 16.5, same as here. And then the sum of x1 squared, you would get that by squaring this value, so making in this table kind of another column here of x1 squared. And then after that, you sum it to get 76.25. Here also, you can basically practice what we are doing in this kind of slide and make sure you get the same coefficient matrix that we see here using the formulas that we see here. So performing basically or solving this set of linear equations, we can solve for A0, A1, and A2 to get the following solution using Gauss elimination or any other method that we learned in the previous kind of lectures to find that A0 is 5, A1 is 4, and A2 is -3, which matches what we see here, basically kind of showing that this approach does in fact work to finding kind of coefficients for multiple linear regression or multiple linear models. Now we're going to move on to interpolation, which is kind of the second part of this lecture, and introducing interpolation, where we're going to start off by looking at kind of Newton interpolation in this lecture, and then in the next lecture, we're going to look at Lagrange interpolation. So the objective of this kind of part of the unit is to recognize that evaluating polynomial coefficients with simultaneous equations is an ill-conditioned problem. So again, if you want to try to solve for coefficients of a polynomial and you're using kind of a set of kind of linear equations, in many cases, the matrices or the coefficient matrix that you get could be an ill-conditioned problem. So instead of fitting all of the data to a linear or polynomial kind of model, what you want to do is basically interpolate between 2 points or 3 points and so on. So also the second objective in this kind of part of the unit is knowing how to interpolate using Newton's polynomial, and then knowing how to interpolate using Lagrange polynomial, and then looking at the dangers of extrapolation, and also recognizing that higher order polynomials can basically have a lot of oscillations that we will see in the next lecture. So starting off with polynomial interpolation, some important things to note here is that basically what we're doing is we're trying to find a polynomial that would basically fit the data points that we have, and we can interpolate between the points that we have in terms of maybe an experiment and or data collected from whatever system that you have. So the main thing here is the polynomial that you fit is going to actually go through all of the points that you have in the data set. And the other thing to note here is if we have n number of data points, then the order of the polynomial is going to be n minus 1. So for example, if I have 2 data points, then I'm going to have a first order polynomial, which is basically a linear model. If I have 3 points, then I'm going to have 3 minus 1 order, which is second order polynomial, which is basically, a polynomial with ending with x squared. And, as we increase the number of data points, we increase the order of the polynomial that is used. And the issue with that, as we said before, is that produces oscillations as we increase the order. So typically, you don't want to use too many points to kind of interpolate between certain data points in a data set. So typically, you want to use maybe 2 points or 3 points kind of maximum, depending on the trend that you see in the data set. So typically in the form that we see here, this is the general kind of calculus form where we have a1 plus a2x plus a3x squared and so on. In MATLAB, this is represented by the coefficients being p1, p2, and so on, where we start off with the order first and then we move on to the next ones. So in MATLAB, you would put the highest x with the highest power to the left first, and then the one with basically the intercept with will be the last value that you put in the matrix representing the coefficients of a polynomial. So there's only one and only one nth order polynomial that fits n plus 1 points. So for example, if I have 2 points, there's only one first order polynomial that would fit these 2 points. Again, if I have 3 points, there's only one second order polynomial that fits these 3 points. And this third example, there's only one third order polynomial that would fit these 4 points that we see here. So let's do an example where we're trying to find what are the coefficients p1, p2, and p3 that would basically kind of interpolate between these 3 points where we have x is equal to 3 and y is equal to 6.16 and so on using drawboard. So let's move to drawboard and perform this example there. So we can find these kind of coefficients using 3 equations because we have 3 unknowns here, p1, p2, and p3. And what we can do is basically formulate 3 equations using the data points that we see in this data set. So for example, using the first row here, we have x equals 3 and f of x equals 6.16. So we can come up with an equation using this kind of model that we have here, this equation, to come up with this model or equation, which is going to be part of the equations that we're going to use to solve for the unknowns p1, p2, and p3. So we have 6.16 is equal to p1 times x squared. In this case, x is 3. So we're going to write 3 squared plus p2, where we have just x, so we have 3 here, plus p3, which is the last unknown. So this is one equation. So we can go and move on to the second equation using the second row that we see here. In this case, x is 4 and f of x is 5.25. So the equation we get is 5.25 equals P1 times 4 squared plus P2 times 4 plus P3. And then using the last row here, we have the third equation, which is 4.57 equals P1 times 5 squared plus P2 times 5 plus P3. So now we have basically a set of linear equations that we can solve using the methods that we've seen in the previous lectures. So converting this into kind of matrix form, we have the coefficients, which are kind of what we see here. So this is 3 squared and 3 and 1. So doing all the math, so 3 squared is 9, and then 3 is just 3, and then just putting 1, we can formulate this coefficient matrix for this given problem. So we have 16, 4, 1, 25, 5, and 1. So this is multiplied by kind of the vector of unknowns. In this case, the vector of unknowns is P1, P2, and P3. And then this gives us, right? So recall this is the format of AX equals B. So now we're going to get the B vector, which is basically going to be just the values that we see on this side of the equations. So 6.16, 5.25, and 4.57. And we can use, say, Gauss elimination to find this, or we can, directly kind of use MATLAB if you've learned how to use MATLAB at this point to solve this kind of matrix problem by doing kind of the equation equals AX equals B and doing the math that X equals A backslash B, which would give us the values of the unknowns. In this case, we would get the values that, P1, P2, and P3 are equal to 0.1150, negative 1.7150, and 10.27. So therefore, the polynomial that goes through all the 3 points is, f of x equals to 0.115x squared minus 1.7150 times x plus 10.27. All right, so now moving back to the lecture. So using the approach that we just did to solve the problem, right, to find the polynomial that interpolates between different data points, as we increase the number of points, we can see that this matrix grows kind of in this form. And this is known as the Vandermonde matrices, which is very ill-conditioned, and that basically means as we perform our kind of solving algorithm for P1, P2, and P3, and so on, and we were going to get basically a lot of round off errors, and hence, the values of P1, P2, and so on are not going to be as accurate as we want. So to solve this, we're going to look at two other methods, which is the Newton polynomial method and the Lagrange polynomial. So today we're going to look at the Newton, and then in the next lecture, we're going to look at the Lagrange polynomial. Another thing to note here, so in MATLAB, if you wanted to find kind of coefficients that would fit a certain basically data set, you would use polyfit and polyval commands to find out what are the coefficients, and you will probably look at those in the lab. So in Newton interpolation, we have, basically the number of points in the data set would affect the order of the polynomial that we developed in the Newton interpolation method. So if we had 2 data points, we would basically develop a first order polynomial, and in this case, it would look at in the format of f of 1x equals to a1 plus a2x. In the Newton approach, it's f of x equals to b1, where b1 is basically the first y value, plus b2, which is going to be kind of a value that we have to derive multiplied by x minus x1, where x would be kind of the variable that changes, which is a value between x1 and x2 that we're trying to find using the interpolation. So as an example, right, when I'm using the first order, what I have is my x values and my y values. And in this case, I'm going to have x1 and x2 and y2 and y1. Sorry, y1 and y2. And what we do is we develop this equation here where b1 is basically the value that we see here, y1. And then b2, we're going to look at how we derive that. And then x would be any value kind of between x1 and x2. And then x1 would be directly equal to the value that we see in the data set. If we had 3 points, right, then we would develop a second order polynomial. And in this case, it kind of gets a bit more not complicated, but a bit of a longer equation where we have this pattern where we keep adding these multiples. So here we had x minus x1, and then here we had x minus x1 times x minus x2, and so on. So we're going to look at how to kind of derive these equations, which is basically using the Newton interpolation method. So one way to look at this is if I had 2 points and we're trying to interpolate between the 2 points, what we have in the Newton approach is that we're using this first point, f of x, as a starting point. And then from there, we add the slope of this linear line. So this is represented by this kind of finite difference, divided difference of f of x2, which is the value here, minus f of x1, divided by x2 minus x1. So that's basically the slope of this linear line times the step size, right? Where we're moving away from x1, and the step size would be basically x minus x1. So if I was moving, this step size away, this is basically my step size, x minus x1. So this is the approach where this is the slope and the finite divided difference that we saw previously in the first kind of topic. So as we move on to higher order polynomials, what we're trying to do here is basically add more terms to the polynomial, so the Newton polynomial. So this here is the first order, where we have the first point, a slope, and then x minus the first point. And then we add a second term here, which is kind of a second order divided difference that we see here, multiplied by these two kind of trailing brackets that keep growing as we increase the order of the polynomial. And the whole objective here is to increase the order so that we get a better estimate if the trend that we see is nonlinear. So the true value here is in black, and it's obviously nonlinear. And if we had a linear model, we would estimate the value of y, right, to be around here for this given x point. But if we had a quadratic, we would move closer to this true value, where we basically use the values of f of x1, f of x2, and f of x3, as we see in this equation, to find out what is the quadratic kind of polynomial or second order polynomial that would give us a better estimate of this interpolation. So the general form for the Newton's interpolating polynomial is what we see here. So we have basically the function f of x equals to the first point, or the value of y at the first point, which is x naught, plus x minus x naught times this basically finite divided difference between the first 2 points. And then we add more terms as we increase the order. So here we have basically a second order finite divided difference. And then here we can have nth order, basically finite divided difference. And we're going to look at an example because it's, that's the best way to learn this approach. But essentially, again, to mention, B naught, B1, and B2. The first one is B1 is, or B naught is just the first point of y. Then B1 is the finite divided difference between the first 2 points. And then B2 would be the higher order, and so on. So let's look at an example. where we are basically trying to find here the first order, then the second order, and then the third order of the finite divided difference using a given data set. So this format here, this table, is an easy way to kind of look at what is the points that we want to find. And in this case, you want to have your data set on the left side first. Then you find the first order, which is going to be combining the first 2 points. And then the second 2 points. So this point and this point, we get this value. And then this point and this point, we get this value. Then we use this first order finite difference to get the second order, and so on. So let's look at an example because that's the best way to kind of learn this approach. So here we have a data set with 3 points. That means we're going to form a second order polynomial because n equals 3. And the polynomial order would be n minus 1. So that means a second order polynomial. So the first step here is to find what is the finite divided difference between these points that we see here. So what we see here is basically this first order difference, which is calculated, right, using this equation here. So we have 3 minus 2 divided by 1 minus 0 will give us this one here. And then we move on to the next part, right, where we're trying to find kind of the second point here. And what we have is this 6 minus 3 divided by 2 minus 1 to get this value of 3 in this table. And that would be for a second order polynomial, all you have for the first order divided difference. Then you move on to the second order divided difference and finite divided difference. And in that case, what we're going to be using is these 2 points here and the endpoints that we see here. So we would have 3 minus 1 divided by 2 minus 0 to get this last kind of second order finite divided difference point, which is a 1. Now we've completed kind of all the calculations we need, and all we have to do is kind of plug those into the equation that we have set up for the Newton's method. So the first point here, B1 would be the 2, then, B0 would be the 2, then B1 would be this 1 here, multiplied by x minus x1. In this case, x1 is 0, plus B2, which is 1, multiplied by, again, x minus 0, which is x1, times x minus x2, which is, in this case, x2 is a 1. So this would be your Newton's polynomial, and then by kind of expanding and simplifying this equation, we would end up with this function x squared plus 2 is the second order polynomial that would basically be used to interpolate between these 3 data points in a data set. So just to mention again, in an exam or a quiz, just getting this equation here is sufficient. You do not have to simplify the equation into this simpler form because it takes a lot of time, and I don't expect you to do that on an exam or a quiz. So we're going to do now an example, right, using Newton interpolating polynomial, which is using these 3 points here on a drawboard. All right, so as we saw in the slides, we first have to start off by looking at kind of the first order difference, where we basically utilize kind of these 2 points first, and then these 2 points second. So just like we saw in the slides, we're going to take this 5.25 and subtract 6.16 and then divide by 4 minus 3. And we get a value of negative 0.91. So in this case, this would be the same as f of, in square brackets, x0 and x1. Then we move on to kind of the second points, or the second and third point, and we perform the same type of approach. So we have 4.57 minus 5.25 divided by 5 minus 4. And we get a value of negative 0.68. Now we have these kind of first order differences, and from there we want to find kind of the second order difference. Another thing to mention here is what we see here is represented in the equations as f square brackets x1 and a comma x2. So now the second order difference is in this case going to be using the points that we see here. So negative 0.68 minus negative 0.91 divided by 5 minus 3. And this will give us a value of 0.115. And this here is the same as f square brackets x naught, x1, x2. And you can see that in a way in this denominator here on the bottom side, this 5 minus 3, what we used is x2 minus x naught. So this is also, as we move on to higher order differences, it's a good way to keep track of what do I need to subtract on the denominator when I have a higher order difference that I'm trying to do the math for. So you always take the last kind of point minus the first point. So as we mentioned before, we take all these calculations, and now we move on to the second order polynomial, right? Because recall that we have, n equals 3, which is 3 points. And because of that, we want to basically develop a Newton interpolating polynomial, which is to the order of n minus 1 as a function of x, which gives us basically, a second order polynomial. So f2x. So that's just one way of kind of remembering what's the order of the polynomial for n given points. So we have the first term is b1 plus b2 times x minus x1 plus b3 times x minus x1 times x minus x2. So here, if you remember, B1 is what we see here. So that's my B1. And then B2 is what we see here. And then B3 is what we see here. So kind of the first row of all this table that we're kind of developing here. So we're going to have this function equal B1, which is 6.16, plus B2, which is negative 0.91, multiplied by x minus x1. In this case, x1 is the value that we see here. So this is, x1, x2, and this is x3. So for x1, we're just going to have minus 3 plus b3, which is 0.115 times x minus x1, which is again 3, times x minus x2, which in this case is 4. And if we expanded and simplified kind of this equation here, the second order polynomial, what you'll find is we get this is equal to 0.115 x squared minus 1.715 x plus 10.27. So what we got is basically the equation that we also got in the earlier approach of using basically the approach of algebra or a set of linear equations to solve this given problem. So again, in this given case, it's exactly the same. In other cases, it might not be, but just to mention that this is the same equation for the same data points that we used in the previous example. So moving back to the slides, here I have an example where we have 4 points. So you would want to develop basically a third order polynomial. So this is a kind of exercise for you guys to try out and find what is the values of or what is the Newton's polynomial for this given data set. So next lecture, we're going to look at the Lagrange interpolation and how that would also relate to the Newton's interpolation, and look at some of the kind of shortfalls of interpolation or extrapolation in this case, and how higher order interpolation methods could result in lots of oscillations in the model or the equation that you develop.